Hi, this video is on Unit 6. I'm covering 3 topics. 1 is on heating and cooling curves, which you can see here. 2 is going to be about Hess's law versus using bond energy, and the third one, or heat of formation versus bond energy, and the third one is about Hess's law. Here we go. So here we have is a heating and cooling curve. First thing I want to talk about is what each of the parts of the curve means. You can see I've identified with solids, liquids, and gases, but I haven't talked about what's happening to the molecules. So here is a solid, all the molecules are really close together. In a liquid, they're a little bit further apart. They've kind of weakened their intermolecular forces, and as a gas, they've completely broken their intermolecular forces. And those phase changes are happening at the flat parts here. The flat parts is where you're changing intermolecular forces, the IMFs. You're not really changing the speed. I'll just say that again. You are not changing the speed. And I know I'm not changing the speed there because my temperature never changes. As I'm going from a liquid to a gas, and changing by vaporizing, my speed of my molecules, average speed of the molecules, is not changing. I know that because the temperature is not changing. So the IMFs are changing. As we go to a liquid to a gas, the IMFs are completely breaking. Now that's different than when we do this bottom part down here, solid to a liquid. You're not breaking IMFs, you're just weakening them or loosening them. And that's important because we can see the distance. This chart is actually not that good. This distance here is not supposed to be equivalent to this distance up here. Really, this chart is wrong in that it should be longer and then go upward. And the reason I know that is because it takes a lot more energy to completely break an intermolecular force to become a gas and not have any attraction at all than it does just to weaken them. And that's true for every single graph. This line here should always be longer than this line over here. The other thing to know about heating and cooling curves is how to do the math. So here I've kind of given you some problems. We can see we've got heat capacity down at this left side, and then the other parts with the heat of vaporization and fusion, and then melting and boiling points over here. Anytime you're looking at a flat part, that's when you're going to use the equation change in H, or enthalpy, equals N moles times change in H. And change in H just depends on what you're doing. Like, is it the heat of condensation, going backwards here, or of vaporization? The other flat part uses the exact same equation. Change in H equals change in H equals N change in H. Or in other words, we could use Q. It really doesn't matter because H and Q in the AP world is going to be exactly the same. In real life, they're not exactly the same, but for as far as we know, it's good enough. The slanted part here, we're going to be using Q equals MC delta T, where it's mass times specific heat times the change in temperature. And that's true of all of the slanted parts. Where the C is going to be your heat capacity. And you're going to use a different one depending on if you've got a solid, a liquid, or a gas. So let's kind of take it with this problem that I've got up here. We're looking at aluminum, and it really depends on what substance you are, because you can see for every substance I have, there's always different numbers. You've got to be careful what substance you're looking at. So here I'm looking at aluminum, and it's asking me solid aluminum at 660. Well, if I look at aluminum on the chart, 660 is its melting point. So 660 is the number right here. And its boiling point is 2450. That's up at this top part. So on the chart, what I'm going to do is I'm going to start at 660 as a solid. That's at this corner right here where the yellow dot is. And I'm going to end, as it says, at 1100 Celsius. 1100 Celsius isn't boiling, because boiling is at 250, so 1100 is somewhere in between. So this is going to be my finishing. So it's going to take me 2 steps to do this. So let's take our Q1, I'll call it. Q1 is this flat part here, where it's actually going from a solid to a liquid. It's melting. And that there, I'm going to be using Q equals N delta H, where N is the number of moles and H is the heat of fusion. So here, N, I have a 5 gram sample, 5 grams. I've got to convert it into moles. So I get out of grams and into moles. On the periodic table, 1 mole is 26.98 grams for aluminum. And I'll multiply it by the H. The H is, for this case, the heat of fusion, 10789. I do that math, and I get 1.999, which I'm going to round it to 2 kilojoules. The second step I've got here is this slanted part. A slanted part needs a C. Q equals MC delta T. Where my M is my mass, 5. My C is my specific heat. I'm in a liquid state right there, so that's 1.05. And then my change in temperature. In this case, final is going to be that 1100 minus my initial, which is at this point down here, 660. If I do that math, I get 2310 but this unit is in joules, because specific heat is in joules. So that means I've got to get both of these to go together. So I'm going to convert this joules into kilojoules by going 2.31 kilojoules. My total is going to be these two added together because it goes over and up, and that's my total. So I get 4.31 kilojoules. And that's my final answer. That's how much energy I have to input in order to get solid aluminum at 660 degrees to 1100 degrees. All right, my next one I'm going to talk about is Hess's law. Hess's law is written for you above here, but the basic idea is if you want to find the h of an equation, you could add up two equations that you already know to find what you don't know. So let's look at this first problem. Here's the equation that I want, and I want to find the change in h for this equation. Hess's law says I can look up a bunch of equations. They've got books of these everywhere. I'm picking these two because they're the most useful, and I can add them up in such a way to get the equation that I want. So here's the way I look at it. I need to have NO2 on the left. So I need an equation with NO2 on the left. Well, I see NO2 right here, but it's on the left. So I'm going to have to flip this one. I'm going to flip it over to make 2 NO2 on the left makes N2 plus 2O2. And because I flipped that, I have to flip the sign of my H. My change in H is now a negative 68 kilojoules. Then that solves my NO2 to be on the left. The other problem I have is I want N2O4 on the right. This equation has N2O4 on the right, so it's good. I want to keep this one just as it is. Then my last step is, according to Hess's law, you can add up the two equations. I'm going to add them up. I'll get N2 on the left, N2 on the right. They're going to cancel. 2O2 on the right, 2O2 on the left. They're going to cancel. So now if I add them, I get 2NO2 as reactants, and N2O4 is the product. And according to Hess's law, if I add equations, I can also add the H's. And when I do that, I get negative 58 kilojoules. Or technically speaking, since that zero is, by how it's written, not going to have a proper sig fig, it's not a sig fig right there, I might want to say that this is actually negative 60 kilojoules using the additive sig fig rules. So if you look at this other problem on the right side, it's the same idea. I want to find the change in H for this top problem right here. So the first thing I want to find is S's to be on the left. Here's an S on the left. I'm going to keep this one as is. Then I want to be able to find O2 on the left. I got O2 on the left here. I'm just going to keep it the way I got it. And then I want to find SO2 on the right. I don't have that, but I've got it down here. So I'm going to flip this equation. When I flip it, I get 2SO3 on the left makes 2SO2 plus O2. And my change in H must then be flipped to be a positive 198 kilojoules. According to Hess's law, if you add equations, you can add the H's. So here I go. I want to look for things that are the same on the left and the right. I've got 2 SO3s on the left and the right. I have O2s. I have 1 on this side and 3 on this side. It's a subtraction sort of thing. So it's kind of like I'm subtracting 1 O2 on this side, which gives me only 2 left over here. So now I've got 2S plus 2 O2 makes 2 SO2. And my change in H is therefore negative 790 plus 198, negative 592. Now this isn't the final equation though, because the problem is I can see here I've got it as SO2 and SO2, and this one is double of that. So I'm going to take this and divide it by 2. Hess's law says whatever you do to the equation, you can do to the H also. So I'm going to divide everything by 2. I'll get S plus O2 makes SO2. That's the equation that I wanted, and so my H is now divided by 2, negative 296 kilojoules. And that's what Hess's law is. The last part that I want to talk about is another way to find H. So real quick, this is one way to find the missing H of an equation. There are lots of ways to do that. Another way to do it is using calorimetry. That's using those styrofoam cups. And you stick the thermometer in there and it goes Q equals MC delta T. You can find the H of the equation for that. That's way number 2. Way number 3 and 4 is the last thing I want to talk about. Okay, here's the third and fourth way to find the H of the reaction. You can use the heat of formation, which is this part on the left, or you can using break minus the make, and that's looking at bond energies. Let's start with the heat of formation. I know I want to use heat of formation here because I've got this little thing with the F on it. You see this little F here? These are the heats of formation. And that kind of tells me I'm going to want to use this equation right here. So the equation looks at products minus reactants. So my change in H is going to be products, all the products minus all the reactants. Here my product is going to be 2 waters. Each water is worth negative 285, so I have to do 2 times negative 285.8. I have to do it times 2 because there are 2 waters, and this number is per mole. There's 2 moles of water. So I'm going to take my water number, 2 of them, plus my CO2, which is negative 393.3, and I'm going to subtract it from all my reactants. One of my reactants is O2. O2 is just found in Earth, like you can just scoop it up. So its heat of formation is 0. You don't have to form it, like God's already formed it for you, so you just have to find it. CH4, I don't know, but according to this problem, I'm trying to find that, so I'm going to call it X. And my change in H in this problem is actually going to be whatever it is on the equation. So this equals negative 889.1. So now I'm just going to do a bunch of math to solve for X, which I have done for you to be 75.8 kilojoules per mole. And there you are. So that's heat of formation. You know you need to do that with these F's. As long as you write down the equation on your note card, you're going to be set to go, I think. The last thing to do is do bond energies. With bond energies, the equation is make minus the break. I'm going to do, sorry, take that back. As you can see what I've written here, it's going to be break minus the make. It's always break minus make because to break bonds, I have to input energy, positive endothermic. To make bonds, I need to output energy. It'll give me energy. That's what'll make me a negative part here. Okay, so let's use our numbers. If you look at the equation above, I am going to break this CH bond right here, this one. I'm also going to break the CCl bond, this one right here. That's how much it'll cost me to break those two. And then I'm going to make a CCl, and I'm going to make an HCl. So I'm going to do that math. Make the break minus the make. My breaks are CH 413 plus the 242 minus the makes 431 plus 328. If I do that math, I get negative 104 kilojoules. So that's the change in H that would be at the end of this reaction. I think if you write down the equations for this one, you're going to be fine. It's hard to remember those, which is probably why you kind of ranked yourself kind of low for it. I hope that helps.